Hi everyone. Today I am walking you through a project I built called the EV system. Basically a real-time dashboard for an electric vehicle that also has collision and blind spot detection, like the safety features in modern cars. Before I get into the slides, let me quickly explain my setup because I refer to these names a lot. I use STM32Cube to actually write code and compile my code. This is the official development environment for STM32 microcontrollers. Think of it like VS Code, but specifically built for programming these chips. The chip itself is the STM32F103C8T6 mounted on a small board called the Blue Pill, popular development board that a lot of embedded engineers use to learn and prototype. It's called Blue Pill because circuit board is literally blue. Now I didn't have the physical hardware wired up with real sensors, so I used PixSimLab, a simulator that pretends to be the actual Blueprint board. It lets me connect virtual LEDs, potentiometers, and sensors, run my compiled code on a simulated chip, and see the results all on my laptop without needing to solder anything. So the flow is I write code in STM32Cube compile it, load it into PixSimLab. PixSimLab simulates the STM32F1R3C8T6 chip running that code, and I can watch it behave exactly like real hardware would. With that context, let's go through how I actually built this step by step. First, this is the EV ADAS system, a real-time electric vehicle dashboard with collision and blind spot detection. This is the EV ADAS system, a real-time electric vehicle dashboard with collision and blind spot detection, built entirely on the STM32F103 C86 Bluepill, simulated in PixSimLab with a live Python dashboard on the other end. So here They, so here the problem. Why did I build this? A real electric vehicle constantly generates data like speed, battery, charge, motor temperature, how close you are to other objects. In a real car, all of this needs to show up on one dashboard, so the driver isn't tracking five different things at once. My goal was to build that entire pipeline myself, starting from the most basic possible step and adding one working piece at a time until I had a full system that streams live data to a Python dashboard on my laptop. So, the first thing I did before writing any real logic was make an LED blink. That sounds too simple to matter, but it's actually the most important first step in embedded development. It proves that STM32Cube IDE, my code, and PixSimLab are all correctly talking to each other. That I can write code, compile it, flash it, and see something happen. It's like turning the ignition key before you try to drive anyway. If the LED doesn't blink, nothing else downstream will work either. And the next step is ADC sensor testing. Once the basic setup worked, I moved to reading real input. A car has pedals, accelerator, and brake motor temperature, and I needed a way to simulate pressing them. I used potentiometers, basically knobs like a volume dial, connected to the chip's analog input pins PA0, PA1, and PA2, PA3. Turning the knob is like pressing the pedal harder or less harder. The microcontroller has something called an ADC, called analog to digital converter, which reads that knob position and turns it into a number the chip can actually use. I use this same trick for accelerator, brake, and even for SOC and motor temperature. And the next one is ultrasonic sensors. Next, I added the sensors that let the car see its surroundings. Three HCSRs for ultrasonic sensors, mounted virtually at the front, left, and right of the vehicle. These work exactly like the parking sensor peaks you hear in real cars. They send out a sound pulse and measure how long takes to bounce back off an object. The longer the delay, the farther away the object was. So we are sensing by using the trigger and echo pins here. Front sensor watches for things ahead of you. Left and right sensors watch for vehicles in your blind spot. And the fourth one is the timer interrupts. Now all of this reading pedals, reading sensors, updating speed needs to happen on a schedule, not randomly. That's where timers come in. Think of timers like a metronome. One timer ticks every 10 milliseconds to update the car speed and battery, and that ticks every 100 milliseconds to check all three ultrasonic sensors. Without this scheduling, everything would run out of sync and the data would be unreliable. Then the next one is EV controller system. With input and timing in place, I built the actual vehicle physics, the part that makes pressing the pedal actually means something. This module calculates motor torque, converts that into speed, drains the battery based on how much power you are using, and even estimates how much driving range is left. I also added drive modes, ECU, normal, sport, something which if I need. We change how aggressively the car responds, plus regenerative braking, where braking actually puts a little large back into the battery, just like in a real EV. And next one is ADAS sensor. I mean ADAS system. This is where three ultrasonic sensors actually become useful safety features, not just raw numbers. I built forward collision warning uh, alerts. It alerts if something is too close ahead, and a time to collision, which is smarter than just distance because it also factors in how fast you are approaching. And the next one is blind spot detection. Alerts if a vehicle is next to you above a certain speed. So I have created this one. And the next one is collision detection. Let me explain time to collision a bit more because it's the core safety logic. If something is 40 centimeters away but you are barely moving, that's not dangerous. But if something is 40 centimeters away and you are approaching fast, that's critical. So I calculate distance divided by your speed equals the time until collision. If the time drops below 3 seconds, it's a warning. Below 1.5 seconds, it's a critical and the system automatically cuts power and stops the vehicle. And the next one is FSM and alarm safety. A real car is not always in the same mood. It's parked, ready, driving, or in a false state if something goes wrong. This is called a final state machine or FSM. Think of it like a character in a video game that can be idle, running, or hurt, and only certain actions are allowed in each time. On top of that, I built a four-level alarm priority system like a hospital triage from P0 to P3. uh, so the most dangerous situation always takes priority over a minor one. And the next one is streaming to the Python dashboard. Here, this is the final piece and honestly the most satisfying part to watch work. All this data like speed, battery, torque, sensor, distances, alarm level gets packed into text messages and sent over UART, which is just a simple wired communication protocol at 115200 bits per second, 10 times every second. On my laptop, a Python script reads those messages and using a library called matplotlib draws them as live animated gauges, a speedometer, a battery bar, and a bird's eye view showing obstacles around the car. This is the moment everything from step 1 to step 8 comes together into one visual dashboard. And here is what I did successfully: real time speed and battery tracking, reliable collision detection with escaping alarms, blind spot monitoring with no false alarms, automatic fault handling on overheating, and fully live dashboard, all running through a simulated blue pill board. So this is the main.c. We have created many files like UART shell C, UART shell.h, and here also common.h, ebcontrol.h, vault, the main, ebcontrol.c. So header files and source files were created. So when we build this one, after successful completion of the build, we go to the PixSim lab. Here, in this PixSim lab, we are using the blue pill board, blue pill board, and the microcontroller is STM32F, F103C86. Here in the modules, we have select the spare parts. So the spare parts looks like this. We have added the potentiometers, virtual terminal, and three ultrasonic sensors and a LED for output. In this potentiometer, so we have acceleration pedal, brake pedal, SOC, and motor temperature. We are using these ultrasonic sensors to detect the collisions like front, left, and right. They can give the output as if the vehicle is too close, it can give alarm. So that we are using the ultrasonic sensors. It also gives alarm senti like when the obstacle is too near, these LEDs will blink, so we can see the output also from this virtual terminal. Like here, this is like this, but when we and this Pixim lab is connected to the STM32. Now we need to print our values into the Python dashboard, so that we are using the we are loading this data into the Python dashboard via UART. So here for Python dashboard, we have written the code. Here I have created dashboard.py for the Python for creating the Python. This is the code. When we compile this by using the command prompt, I mean in this terminal, we have implemented EV controller ADAS system. We identified the fault and also the FSM and the alarm system. So we have done all these things. So now we need to send this whole data from the Pixim lab to the Python dashboard via UART. So that I have created a code and I write the code in the Visual Studio, and I need to compile that code. So I'm I created dashboard.py in the VS Studio. After this compilation, it will directly open to the Python dashboard. It looks like this. So this is the real-time dashboard. We are using the COM4 and COM1 ports here. In the Pixim lab, we are using the COM4, and here we are using the COM1. So we giving the connection to both of them, so that we can see the real time data in like this in the Python dashboard. So when we can also check the values by changing the potentiometers, like these are the potentiometer values. When we change here, we can also observe the graph is also changing, and the torque acceleration changes when we when we increasing the when we increasing or decreasing in the potentiometers, it will automatically shows the changes in the Python dashboard, because these two are connected via COM4 and COM1 ports. Now we are applying the break here, so we're also getting changes. Yeah, so I have built this Python dashboard here, and this is the ADAS bird eye view. The vehicle is not too close, so that we don't have any warnings. If the vehicle is getting close, we can get that warnings like advisory or critical. Here it is far away from the vehicle, so that way the mode is normal only, and then alarm was also none, because there is no problem with these distances. So here in this also we can have the left, right, and front distances, so the both distances were not dangerous, so it's okay. And this is the board, and this is the final output. So that's the full journey from a single blinking LED to a complete real-time EV safety dashboard. So we built a UV dashboard system.